Okay, chemistry, here it is, the last section of chapter 22, page 701, section 4, organic reactions. So far, we've just talked about organic molecules. And this is just going to scratch the surface as to how reactions can take place and names for the different kinds. So you're going to need to know some of the different kinds. First one is a substitution reaction where one or more atoms replace another. When you're playing basketball or football or something like this, when someone goes to take the place of another player, we call that a sub. Well, same thing works here. So if we have, say, methane here, we can take one of these hydrogens off and put a chlorine in its place. This hydrogen was just substituted. So this is called a substituted hydrocarbon. All right, substitution reaction. And you can see a demonstration or an illustration of it here in your book. Now we could keep on doing that. This would be chloromethane. You can get to 2-chloro and trichloro. Trichloromethane is known as chloroform, sometimes used to put people to sleep. Tetrachloromethane, that's 4 chlorines all the way around, is well known as carbon tetrachloride. It's actually pretty nasty stuff, but it's a common molecule in chemistry. And you can see how the substitution continues. It could be substituted with fluorine, chlorine, bromine, so on. Other things could substitute in there as well. So anytime one takes the place of a hydrogen, it's a substituted hydrocarbon. All right, something that comes a little closer to home is an addition reaction. The reason is because, first of all, we have a molecule that has it's an unsaturated molecule, has a double bond, and that means it could handle some more hydrogens. So what we could do is we could add some more hydrogens to this molecule. To do that, we would need to break this double bond and add a hydrogen here and here. Since I'm still using the flexible bonds, it looks a little funny, but now we are saturated, all single bonds. And so this process of adding hydrogens to it is called hydrogenation. Maybe you've heard of it because it talks about when we take vegetable oils from plants, and oils from plants are unsaturated. These are better molecules for you because even though you can't tell in this picture, when we do double bonds, that makes the molecule bend. It is so much more healthy for you to have bent molecules in your body. So this is why vegetable oil is much better for you than, say, animal fats. Animal fats tend to be saturated. But when you're making your toast in the morning, you don't like to pour on your fat, your oil, to your toast. You want to spread it on. Maybe then it can melt. But you don't want it to be melted until you've put it on your bread. So this is why we want to add some hydrogen so we can get more of those London dispersion forces happening, and so we can form a solid room temperature. General rule of thumb is that if it is unsaturated, it is a liquid at room temperature. If it becomes saturated, so we get more hydrogens bonded in there, it becomes a solid at room temperature. Now, there's a lot of explanation that I would give you if you were here, but in a nutshell, you are what you eat. Your body, this book actually has in the margin here talking about how your body takes the fat and puts it into your cells. You might remember from biology that your cell walls are made out of, or cell membrane is made out of a phospholipid bilayer. This bilayer, which has molecules like this, are either straight or they're crooked. Straight ones pack really tight. There's not much room in between them. This makes it hard for your insulin to get the sugar across the cell membrane, and you can become diabetic. If they're more bent and crooked, they don't stack so well, and so then there's holes that allow for more flexibility and space in between the molecules, and the insulin is able to come into the cell much more readily, and you don't have type 2 diabetes. So type 2 diabetes is actually more of a fat problem and not so much a sugar problem. It causes a sugar problem, and sugar can turn into fat. So the reason why trans fats are bad is because what happens is in this process, you see there's 2 double bonds here. In fact, there's more than that. But we might hydrogenate several of them, but we might not hydrogenate some others. Well, the cis bonds are bent. But in the heating up and the catalytic process, these can rotate and become straight, even though they're unsaturated. So trans fats, you've probably heard of, are not so healthy for you for the same reason, at least some of the same reasons, that saturated fats are not good for you, because they make your cell walls not so flexible. So we recognize that in this country, and more they're making it illegal to have trans fats. Why? Because you can't. That takes out the vegetable oil competition. But I don't expect to see us making any laws against saturated fats, even though they're also not good for you, because who's going to give up making ice cream and cheese and all those things, because those have so many saturated fats that to make saturated fats illegal would basically make it illegal to eat meat or eggs or cheese, and that would force everybody to be vegetarian. I don't see that happening anytime soon, but we can pick on a few small things like trans fats and say, okay, I feel better because there's no trans fats. Really, to make a difference, you need to reduce your saturated fats, which is mostly in animal products. Now, some plants do have saturated fats. In fact, all plants do have some, or most of them do. Avocado, coconut, and so forth is a little higher in saturated fat, but compared to animal products, it's small, and you're okay to have some saturated fat. You just don't want to have a lot of saturated fat. And plants have a nice balance of saturated versus unsaturated fats. And the process of making a unsaturated saturated is to go through a process of hydrogenation, and when it's finished, we say that the product is hydrogenated because it's got more hydrogen in it. All right, some other reaction types are condensation. Now, when you hear the word condensation, you probably are thinking water. Well, that's exactly what's going on here, because 2 molecules each have on them, one end has the carboxyl group here with an OH, and this end has a hydrogen, in this particular example, 2 amino acids. Amino acids are the building blocks of proteins. There are 20 different amino acids that your body needs, and it uses these to build a protein. So in order to do that, it's like taking a train car and putting it together, and this is the locking mechanism. The OH joins with the H, and it forms water. These 2 guys come together, and a water comes out. This is why it's called a condensation, because water comes out. And now they're connected here, right here, and no water's in between. Now you can see that there's another carboxyl group here on this side, and this process can continue on and on. Biologically, we do not consider a molecule a protein until it has at least 50 amino acids. Your hemoglobin molecule in your red blood cell has 600 amino acids to make one hemoglobin molecule to collect your oxygen. And these have to be in such a particular order that those that have sickle cell anemia have only 3 of these amino acids are wrong out of the 600. Now, if you took a test and only missed 3 out of 600, you would say you did pretty good. That should be worth an A. But in your body, if your hemoglobin is missing 3 amino acids, or I should say has the wrong ones, you have sickle cell anemia, which means that you're never going to be playing sports, hiking up mountains, or things like this, because your body can't absorb oxygen because, well, it actually absorbs it, but the cells can't go through the capillaries because they're shaped the wrong way. They're shaped like a C instead of an inner tube. But this is the process, the condensation reaction that goes along for making proteins. Another kind of water reaction is elimination. Now these are very similar, so pay close attention. This is where you have a molecule of water that comes out from adjacent carbons. Notice this one was from two different molecules. This one is on the same molecule. So we could have a molecule of ethanol, and it could break apart to form ethene and water. And that's elimination reaction. Now, if you were here, I would do this demonstration for you. This is sugar, and you can take some sulfuric acid and put it in there, stir it up, and it will react and eliminate the water out of the sugar, or the hydrogen oxygen, produce water, which you're going to see in a reaction as steam, and leave behind what? Just the carbon. And this is kind of a cool reaction to watch. I really encourage you to take a look, type it into the internet, sugar and sulfuric acid, and watch it. It's a slow reaction, and if you want to get a little more for what it's really like, as you watch it, put a piece of cinnamon raisin toast in the toaster and toast it and set it on high, maybe burn it just slightly, and that's what it'll smell like. This smells like burnt raisins. And every year when I do the demonstration, students tell me, oh, how could it possibly smell like burnt raisins? And then when we do it, oh yeah, it smells like burnt raisins. So, kind of fun reaction. Look it up on the internet and watch it. It's a great one to watch. It just slowly grows. That's elimination reaction. So compare elimination with a condensation reaction and know and understand the difference between the two. Next one, forming polymers. This is so important in our world, as are these other reactions. In fact, a condensation reaction is using monomers to form a polymer. A protein is a polymer. So that's why they say here polymers are all around us. The food we eat, how is it, could it be in the food? Starch. So your bread, your rice, and things like this, potatoes, they have starch in them. They are polymers. They are sugars combined one right after the other, one click, click, just like the proteins are here. Hundreds and thousands of sugar molecules bonded together make starch. Cellulose is another network of sugar molecules, and that's what makes up all the plants' cells and so forth. So they are, you look outside the window and you see the grass and the trees, you're looking at a lot of cellulose. So you might ask, well, why, if it's all made out of sugar, why isn't it sweet? Well, it's bonded closely together like this. The sugar that's sweet is when you break apart the molecule and you have it by itself. So the cows can eat the cellulose and digest it, and you can see why they get so much energy from it is because it's just sugar bonded very strongly. When it comes to eating, sugar digests so quickly and easily that it's gone like a piece of paper on the fire. Starch is like having a log and you put it on the fire. It burns as well, but it burns slowly and steadily. So this is the food that you want to eat the most of. Proteins are also polymers, just as was demonstrated over here. Just like a train, you have 50, 600, whatever, amino acids connected together, one piece after another. Now, these small units are called monomers. So here's a monomer, and here's a monomer. And then a polymer can be made from identical or different monomers. A polymer made for two or more different monomers is a copolymer. So here are two identical amino acids. Usually it doesn't come together that way, but if it's the same, we just call those monomers. Now, if they're made by two or more different ones, which in fact proteins are, because they're made out of 20 different ones, then it's going to be a copolymer. Your clothes are made out of them, as we're going to look at in the next page. Another type of reaction, addition polymer. So here we can take something like ethene with a catalyst to help this along, and we can click these things together just like train cars as long as we want, and then we just have a whole lot. Instead of calling it mono, di, tri, whatever, it's going to be so many, we're going to call it polyethylene, and you've probably heard of polyethylene. In fact, there's probably hardly a day that goes by that you don't use polyethylene because it's in plastic bottles, plastic bags, cartons, crates, things like this. And depending on how they tweak it just a little bit with the molecules, you can get what's called HDPE, high density polyethylene, low density polyethylene, and so forth. And this is one reason why when it comes to recycling, they need to know what kind of plastic it is, which way it's arranged to get it to match its proper connection. A condensation polymer is a polymer formed by the condensation reaction, which we talked about on the other page. Probably one of the most famous polymer productions is when you take this one here, and I encourage you to read about this, but here's hexadiamine. So amine meaning there's two nitrogens here, and a diptic acid. These two get put together and click like this, one right after the other. Notice that there's 6 carbons in each of them, and so this got to be called nylon 66. One of the most commonly used products that man makes synthetically. Also, this is the process we use to make polyester, and by tweaking what molecules are on here, what atoms are on here, we can make all kinds of things, just slightly changing things and the reactions for them. All right, that concludes this section, this chapter, and I really encourage you to just type in the internet to look for this reaction. It's kind of a fun one to watch, and that concludes the section. Do your homework. Keep up the good work.